Welcome linear algebra fans, a video today on linear transformations. So in this video we'll start with a definition, see the definition of what makes a transformation linear, talk about some terminology. We'll talk briefly about cartoons that represent linear transformations. We'll use those pretty frequently. We'll see that matrices are linear transformations. Soon we'll see that linear transformations can be also represented by matrices. It's pretty cool. We'll see how linear combinations act under linear transformations, talk about preimages, and then talk about a couple different ways to cook up a new linear transformation from an old one. So first, a definition. Linear transformation is T. T takes elements in the vector space U to the elements in the vector space V. U is called the domain, V is called the codomain, and it has two properties. The first property is that the transformation of a sum is the sum of the transformations. And the second property is that the scalar multiple of a transformation is the transformation of the scalar multiple. Okay, so in each of these statements, there are elements of vector addition and scalar multiplication. And where that vector addition or scalar multiplication occurs depends on the vector space. Okay, so when we describe u1 plus u2 or alpha times u, those are operations in the domain, the vector space u. On the other hand, when we talk about t of u1 plus t of u2 or alpha times t of u, those are operations in the vector space v, or the codomain. Okay, we generally refer to t of u as the image of u, right? T of u is an element of the codomain v. Okay, so here's an example. Let's have a look at the function that takes a vector from the domain C3 to the codomain C2 given by t of x1, x2, x3 is equal to 2x1 plus x3 and negative 4x2. Okay, so we'll go ahead and show that this is linear by having a look at the image of x plus y and the image of alpha x. So we know how to do vector addition in C3. We see that the image of x plus y is 2 times x1 plus y1 plus x3 plus y3 and minus 4 x2 plus y2. Now, of course, we can break that up and we can see that t of the sum, t of x plus y, is t of x plus t of y, right? And again, this second operation is vector addition in C2 in the codomain. Okay, it's similar for scalar multiplication. Okay, we see that, again, the image of alpha x is alpha times the image of x. So these two computations, right, the image of the sum is the sum of the images, and the image of a scalar multiple is a scalar multiple of the image. These show that the formula for t, that transformation t, is linear. Of course, if there are some transformations that are linear, there are some transformations that are not. We can see quickly that this transformation is not linear by just picking a couple of elements from C3 and showing that, for instance, the image of the sum is not the sum of the images. Okay, it's a pretty quick computation to show that t of x is 602, t of y is 1206, and t of x plus y, which would be t of 333, turns out to be 18010, which is not t of x plus t of y. So the image of the sum is not the sum of the images. This is similarly true for scalar multiplication, and I won't go through it, but maybe I'll let you cook up an example. Okay, so this works in other vector spaces also. Let's go ahead and have a look at the linear transformation from domain P3 to codomain M22 given by this formula. We're going to show that t is linear Okay, so with p equal to a1 plus b1x plus c1x squared plus d1x cubed, and similarly q with a2 plus b2x plus c2x squared plus d2x cubed, we can quickly compute p plus q and alpha p. These are elements in P3. And then we can have a look at the image, for instance, of p plus qx. Now we know that vector addition or matrix addition can be broken up in M sub 2, 2. And once we break up that vector addition in M sub 2, 2, we can see that this is exactly the image of P plus the image of Q. And it works the same way with the image of alpha P. Okay, we see that the image of alpha P has just an alpha A1 plus alpha B1, alpha A1 minus 2 alpha C1, alpha D1, and alpha B1 minus alpha D1. Of course, in M22, we know how to pull that alpha out. And once we do that, we see that the image of a scalar multiple is a scalar multiple of the image. This shows that, again, T is linear. Okay, here's an opportunity for you to play with the linear transformation. Here's a transformation with domain P4, codomain P5, and it ends up that this is a linear transformation. So I'll let you work that out on the worksheet. Here's the theorem. Suppose that you have a linear transformation, then the image of the zero vector is always the zero vector. The proof of this is pretty quick. Okay, since our transformation is linear, it must be that T of alpha u is alpha T of u, and that has to work for all alpha. So in particular, it has to work when alpha is 0. So certainly T of the zero vector for alpha equals 0 is T of alpha u. Is alpha T of u. Now since alpha is 0, this had better be 0. Okay, so we see that in a linear transformation, the image of the zero vector always has to give us back the zero vector. Okay, as it turns out, this can be a quick check maybe for not linear. If you have a look at the image of the zero vector and you don't get back the zero vector, then this theorem says that your transformation is not linear. Okay, so here's an example revisited. We see that the image of the zero vector in C3 is not the zero vector. So immediately we can conclude that this transformation is not linear. Okay, talk for a second about cartoons. We often represent these linear transformations with cartoons. So here's what I mean by that. U and V are both vector spaces, therefore they both have a zero vector in their vector space. We know that the zero vector in the domain always maps to the zero vector in the codomain. Okay, it might be the case that the image of this vector u1 is some vector v1 in the codomain. And it might be the case that this other vector u2 also maps to the zero vector in the codomain. Now it might be the case that there's a vector v2 that has nothing in u that maps to it, and we'll talk about that later. Okay, so in any case, these cartoons are useful to illustrate linear transformations. It's sort of mathematical tradition to write the vector spaces as kidney beans for some reason. We'll talk about this a little bit more as we go on. Okay, let's talk about matrices and linear transformations. Here's an example. Let's take the matrix A to be the transformation from C4 to C3 given by P of x equals AX. It turns out to be pretty quick to show that P is linear in this case. Okay, so when x and y are elements of the domain C4 and alpha is a scalar, we know that the image of the sum x plus y is the matrix A times x plus y. Of course, this is just AX plus AY, which is the sum of the images. Similarly, the image of alpha x is A times alpha x, which is alpha times AX, which is exactly alpha times T of x. So the image of a scalar multiple is also the scalar multiple of the image. Okay, this always works for any any matrix A, and the proof is like what we just did before. So the take-home message here is that whenever we can express a transformation from Cn to Cm by matrix multiplication AX, then that transformation is linear. Okay, it's going to be important to be able to pick off a matrix B such that R of X equals Bx. Here's an example. So we know how to do this just with a coefficient matrix. So when B has first row 2, minus 3, 4, second row 1, 1, 1, third row minus 1, 5, minus 3, and fourth row 0, 1, minus 4, then R of X is Bx. So since we know a transformation from Cn to Cm defined by matrix multiplication is always linear, we know that our transformation R is linear. Okay, it turns out that any linear transformation from Cn to Cm can always be represented by matrix multiplication. Okay, the proof here is constructive, and it not only shows us how to prove the theorem, but it also shows us how to cook up the matrix A. So when B is the standard basis for Cn, we know that any vectors x and y that are elements of Cn can be written as linear combinations of those standard basis vectors. Also, any scalar multiple of x can be written as a linear combination of those standard basis vectors. Now, moreover, we know because the transformation is linear that the image of the sum is the sum of the images, and the image of a scalar multiple is a scalar multiple of the image. So all that's left then is to write down what the image of the sum is, the image of the scalar multiple is, and that's going to tell us how to cook up the matrix A. Okay, so I won't go through all the details here, but it turns out that if you take the matrix A to have columns that are the images of those standard basis vectors in the domain, then the matrix A is the matrix that does the job. Okay, so I'll point out here that this matrix is exactly how we would cook up a matrix A that is the matrix of the linear transformation. Okay, so one thing we'll do pretty frequently is come up with that matrix of a linear transformation by looking at the matrix containing the images of the standard basis vectors in the domain. Okay, so here's an example. Let's go ahead and check out this transformation S from C3 to C4. Now, if we look at the image of the basis vectors in C3, we can come up with the matrix of this transformation pretty quickly. Okay, so here are the images of those standard basis vectors in C3, and we can see that when those images are the columns of a matrix C, that matrix C is the matrix of the linear transformation. Okay, so this allows us to identify the image of say, this element Z in two different ways. On one hand, we could find the image of the element Z by thinking about Z as just 2 minus 3, 3 in C3. Okay, and if you work out the linear algebra here, the matrix multiplication, what you get is 27, 2, 39, and minus 12. Now, on the other hand, we could also write Z as a linear combination of the unit vectors in C3, and since we know their image, we know how to identify the sum of those linear combinations. And not surprisingly, looking at the sum of, the image of the sum as the sum of the images, we see that we get the same answer, 27, 2, 39, and minus 12. Okay, so that turns out to always be true, that you can always take an image of a linear transformation, and it's, an image of a linear combination, and it's the linear combination of the image. Okay, and that's a theorem. to prove this theorem, we'll just go ahead and write it down. Okay, since T is a linear transformation, first we know that the image of a sum is the sum of the images. Moreover, since T is a linear transformation, we know that the image of a scalar multiple is a scalar multiple of the image, and we see that the image of a linear combination in general is the linear combination of the images. Okay, this is super useful if we have a basis, and I'll state this theorem without proving it, but the theorem is that if you know the action of your linear transformation on a basis, then that linear transformation is uniquely defined. Okay, again, we know that when B is a basis, all elements of the vector space U have a unique representation with respect to the elements in B. Okay, so again here the take-home message is that if you know the action or the image of each basis vector, any basis now, on the image of a linear transformation on each basis vector, then that linear transformation is uniquely defined. Okay, so here's an example. Let's go ahead and have a look at some linear transformation for which we know that the image of the first basis vector in C3 is 2, 1. The image of the second basis vector in C3 is -1, 4. And the image of the third basis vector in C3 is 6, 0. We can certainly then find the image of this vector 2, -3, 1 because we know how to write 2, -3, 1 as a linear combination of standard basis vectors in C3. Okay, so again, here our vector W is 2 times the first basis vector plus -3 times the second basis vector plus 1 times the third basis vector. We know that the image of the sum is the sum of the images. More generally, the image of a linear combination is a linear combination of the images. So we can just compute that linear combination of those images and get out -10 and 13. Okay, I'll give you a chance to try this with the vector x to compute T of x just based on a linear combination here of x in terms of those standard unit vectors. Now, this works if you have a non-standard basis too. So here I'm taking D. D, I didn't write this, but D is the set of vectors containing this one, -1, 5, 1, and 3, 1, 4. It turns out that D is a set of 3 linearly independent vectors in C3, therefore it's a basis. Okay, you should check this, but in any case, we can compute R of y as long as we can write y as a linear combination of these elements in D. So the first thing we have to do to answer this question is identify that our vector y can be written as a linear combination of these 3 vectors in D, this non-standard basis. Now, in general, of course, in order to do that, you have to solve a linear system, but not such a big deal. So the linear system you would solve is a 3 by 3 linear system. Once we know that the image of a linear combination is the linear combination of the image. This should be R instead of T, but in any case, we know that R of y is 3 times R of the first vector plus -2 times R of the second vector plus 1 times R of the third vector. And since we know the image of all of those vectors, we can quickly compute that the image of the linear combination is the linear combination of the images, so you get 17 minus 8. Okay, I'll give you a chance to try this on your own with a different vector, this vector z that's 0, -2, -3. So see how that goes, and we can talk about this one in class. Okay, this works in other vector spaces too. In other vector spaces, we'll go ahead and have a look at a subspace of polynomials of the vector space P3 such that P of 1 is 0 and P of 3 is 0. Okay, so here's a basis. You should check that this set given here is a basis for that subspace. And let's suppose that we know the action of a transformation S that goes from P3 to M22 on each of those elements of the basis. Okay, then we can pretty quickly figure out what the image of this new vector Q is, as long as we can write Q as a linear combination of the vectors in our basis. Okay, so it's fairly quick to see what that linear combination has to be. Okay, it's pretty quick in this case to see that Q has to be minus 5 times the first basis vector plus 2 times the second basis vector. Okay, so the image of the linear combination is the linear combination of the images, so we can see then quickly what the image S of Q is. Okay, and here's that image, negative 5 times the image of the first basis vector plus 2 times the image of the second basis vector ends up being minus 5, 17, minus 8, 0. Okay, so again, here knowing the image of a transformation on a basis of a vector space uniquely determines that transformation on that vector space. Okay, let's talk for a minute about preimages. Here's the definition. Given a linear transformation, we can talk about the preimage of an element V of the codomain as a subset of U. It's all of the vectors U that map or that have image V. Okay, so you can imagine it may be the case that there's only one element in U that maps to V. It may be that there are a whole bunch of vectors in the vector space U that map to the vector V, or it may be that there are no vectors that map to or have image V in the vector space V. Okay, so this should be familiar to you. It turns out that determining a preimage is always the same as solving some linear system. Okay, so let's go ahead and have a look at this example. Let's find the preimage of this element V in the vector space C3, right? So the preimage is a subset of C3. Okay, so we're looking for all U's such that T of U is equal to V. Okay, so if we're looking for U such that T of U is equal to V, or T of U is 2, 1, 3, 2, then we can see that it better be that A minus B is 2. It had better be that 2A plus 2B plus C is 1. It had better be that 3A plus B plus C is 3, and minus 2A minus 6B minus 2C is 2. Okay, so we can set up a linear system that represents the system of equations. We can augment, row reduce, and we can see that there are a whole bunch of U's that satisfy this equation. Okay, so whatever the solution of this system is the preimage of this element V. We can play the same game for a different element W in M22. And when we go ahead and write down the linear system, you can imagine it's sort of similar with a different vector of constants, row reduce, row reduce, row reduce. And it turns out in this case that the last column is a pivot column in our augmented matrix, the row reduce form. And this tells us that the preimage of this element W is the empty set. Okay, so again, when the linear system has no solution, there is no U in the domain C3 that maps to or has image of W in M22, so the preimage of W is the empty set. Okay, so we'll close up cooking up a couple new transformations from old transformations. We'll see how to do this. Let's suppose that T and S are linear transformations, then their sum is a linear transformation as well. Okay, so I won't go through the proof of this, but we just show that the image of the sum is the sum of the images, and the image of a scalar multiple is the scalar multiple of the image under this new addition. Okay, so I'll just refer you to the book here, but it turns out that you can talk about a sum of these linear transformations, and it should remind you a lot of the sum of the corresponding matrices. Okay, similarly, given a linear transformation in any scalar, the scalar multiple is a new function that's also a linear transformation. Okay, so I won't go through this in any great detail either, but you can pretty quickly compute the transformation 2t, for instance, for this transformation, and it ends up being linear. Now, here is the theorem that blows your mind. If you think about U and V as vector spaces, then the set of all possible linear transformations from U to V, because it's closed under vector addition and scalar multiplication, right? The image of any sum is the sum of the images, and the image of a scalar multiple is the scalar multiple of the image. This collection of all linear transformations itself is a vector space. That's pretty wild. Okay, one final linear transformation, the composition. So the composition of linear transformations ends up being linear also, and I won't go through the proof here either, but it turns out in terms of matrices and matrix representations that the composition is exactly matrix multiplication. Okay, so I'll leave that to you also, but these are 3 different ways to cook up new transformation from old, taking sums, taking scalar multiples, and taking compositions. Okay, folks, I hope you'd enjoyed this video on linear transformations. A lot going on here, but we'll have a closer look at these linear transformations in our next couple sections. Have a great day, and we'll talk to you soon. Bye-bye.